Hi everyone, welcome to zkWarsaw 16. A quick heads up, we are recording and live streaming this. The format for today is like our usual monthly meetup. We will have one, in this case two, talks by Rafał, giving us a teaser intro into the technicalities, and then the main keynote talk by Mina's CEO. Other than that, we will be ending up with a bit of networking. We'll have some pizzas. I'm told we have twice too many pizzas tonight, given the big show up according to Luma. Feel free to grab some. Now, I'd like to thank our partners, the Ethereum Support System Ecosystem Support Program. I need to learn this, ESP, and Vilaya. And I'd like to give you a quick heads up that there will be a second full-day conference coming up this year, like we were hoping, and we have the date set. It's going to be the 4th of September. So stay tuned for that. And we have a little... Do we have a QR code?
Next slide.
Yes, so feel free to scan this and tell us if you're interested in joining the Verifiable Summit on September the 4th. We might have some first-comer gimmicks. Other than that, I would like to hand over to Rafał to give us a quick intro.
Hey, hi everyone, and thanks Horace, thanks Gosia for the opportunity to come here and speak today. So my name is Rafał, and I work in crypto I'm not working in crypto yet, but I'm interested in crypto for around 2.5 years right now. I have background in economics, and after 7 years in consulting, I'll be joining Vitayer shortly. So actually on Wednesday, so the day after tomorrow, and I'm super excited about it. So it will be a good warm up for me, this presentation. We'll speak about cryptographic commitments, and Gosia asked me that for this presentation to be rather straightforward, not very difficult to understand, and I hope it will be, but it went south a bit at some slides, so let's see how it goes. The agenda for today is we'll talk first what cryptographic commitments are, and then we'll go through the types of some of cryptographic commitments used in crypto and not only. Okay, so cryptographic commitments, what they do, they allow to commit to a message or a value without revealing this message or value, and later to prove that it hasn't been changed or tampered with. So we have Alice. Let's give a real world example. And Alice has a message, and she would like to commit to it. This is Bob, by the way. And to commit in the real world, we could use an envelope, just pack the message to the envelope and send to Bob. So this is what Alice do, and the commitment is ready because the document is sealed in the envelope. The commitments have two properties, and this is for all the types of cryptographic commitments. So no matter it's like polynomial or Pedersen commitment or any others. So first is binding, which means that Alice cannot change data once the data is committed to. And this requirement is met because when she packs the message to the envelope and handles it to Bob, then she cannot change the message. The next is hiding. So the commitment cannot reveal anything about the data that's included in the on the document, and this requirement is also met unless, of course, the envelope is transparent, which is usually not the case in the real world. Okay, so this was a quick intro, and now we'll discuss the first type of commitments, hash-based commitments. So what we need first is a collision-resistant hash function. For example, SHA-256, and collision resistant means that for a given input, then for a given input, the output is for two given inputs, the output will always be different, so they cannot give the same output, or there is like a very small chance that they will give the same output. And the commit algorithm to this kind of hash function would take the data and the randomness as input, and it would output the commitment value. We'll see in a while how it could look. And the verify algorithm would be to take everything together, so the data, the commitment, and the randomness, recalculate the commitment, and compare both together. So with our Alice and Bob example, Alice has a message to Bob, and she generates some randomness and calculates the commitment and handles everything to Bob. Bob takes the hashing function, recalculates, and outputs true or false, depending whether the commitment is the same as provided by Alice. The first example was quite simple, so right now we'll speak about Pedersen commitments, and they're slightly more complicated. So first, for Pedersen commitments, we need a cyclic, they are calculated in cyclic groups. So we need a generator G that will generate all the elements in the group. So G1, G2, G squared, G to the third, all the way up to G to P minus 1, where P is a prime. And everything will happen, the calculation modulo the P. So it may look complicated, but in fact, basically, those two things are equals. So in cryptography, we'll see that we'll have the group including those integers all the way to this prime minus 1. But all of them will be generated by these powers of G. And the commit algorithm would be also quite simple. So we'll take the generator G, we will take another element of the group, which is H. It's also the element of the group G. We'll take the value, so value from the group as well, and the randomness also from the group. And this type of commitments have a very nice property, which is homomorphism. So it means that given two commitments, we can multiply them together and output another commitment. So in the example of this group, it would be quite simple. So we have G to the power of I and G to the power of J, and if we multiply them together, it would be the same as we added G to the I to G to J. Also very simple math here. Those types of commitments are, as live example, are used in Monero. So this blockchain which is focused on privacy, and they are used to hide the amount of the transactions. And if we take the example of Alice and Bob, so we have Alice, and first there would have to be a setup run ahead of making any transactions. So would have a prime, which would be 17, and generator G for the group, and another element of the group 3. There is no Bob this time because it's privacy preserving blockchain, so we don't have Bob anymore. And transaction, this may be sent to Bob or to anyone else. The value of the transaction would be 10 Monero, and let's say the randomness would be 5. So how would we compute the commitment to such a transaction? Very simple. So we have the equation that we discussed before, which would give us, after all the calculations, 11. And this commitment would be sent by Alice to transmitted to the blockchain, where it would be picked up by the validators and added to the blockchain. How validators would verify the transactions? This is slightly more complex, and I'll not go into it. Honestly, I don't really understand how this would work, but this is here they use bullet proofs, so to make sure that Alice has at least the amount of the currency that she wants to send.
Is the randomness value set for each transaction randomly?
Yeah, it would be, yeah. So if we take the trivial example as we had before with the hash-based commitments, we just take and reveal all the values, so the commitment and the transaction data, and then we could review the commitment. But it would be less useful, of course. With this, we came to polynomial commitments, which are of probably the most interesting of all of the examples that I've given today, and widely used in zk. All right, so when we have a snark, we have two ingredients, or two parts of the snark. So we have first arithmetization, and in the arithmetization, we take the program or the calculation or computation that we want to prove, and we turn it into a polynomial. There are a few ways to do that, and then we take this polynomial and we have to commit to it, calculate the proof, and send it to verifier to verify. Just a reminder, what is a polynomial? So this is a mathematical expression that looks as follows. So p of x equals to a of x to the third, b plus b of x to the second, etc., where a, b, c are coefficients of the polynomial. So for groups or prime fields, it would be integers only. So we have, for example, 52, or 5 or 3. The coefficient could be an integer. So there is a nice property for polynomial commitments. First, it's the polynomial itself doesn't have to be revealed, and the proof, which is calculated based on a snark, is usually much smaller than the polynomial itself. In a typical snark, the goal would be for a prover to convince the verifier that he knows the polynomial that he calculated in this part, meaning the arithmetization. Okay, so real world, I guess it's used in Mina, of course, and VLayer as well. There's many other examples, and basically all snarks are based on polynomial commitments. Right. So then, what would be the commit algorithm for this kind of commitments? So we have the prover, which would evaluate the polynomial at a random number r, and in KZG polynomial commitment, so this is one of the most widely used polynomial commitment schemes. There would be an SRS generated. It would be basically a secret point on an elliptic curve. And here we'll of course not discuss the elliptic curves and any similar complex concepts because Gosia asked us not to go into this direction, so we simplified very much, and it wouldn't be useful for cryptographic purposes. But my goal here is to show you how the prover would calculate the proof for the polynomial and how the verifier would verify that the prover indeed knows this polynomial. So let's go. Oops. The proof algorithm here would be the claim of the prover that at a certain input the polynomial p of x equals y, and he would create a proof of it. He would send this proof together with the commitment and the y amount to verifier. And the verifier algorithm would be for the verifier to validate that polynomial evaluated at some x equals y, based on the input provided by the prover, and also that the commitment which is provided separately, indeed corresponds to P of x. So we have Bob and Alice once again, and let's try to play this verify game with them. So the commit algorithm would be for Alice. Alice wants to prove that her polynomial, which is here, P of x equals x squared minus 1, very simple polynomial, equals 0 when we evaluate x equals 1. And as we see, if we put here 1 minus 1 is 0, so the polynomial would indeed evaluate to 0. So she commits to this polynomial, but by evaluating it at a random number r. In true case, it would be number from, or like secret value calculated in the trusted setup. So in this case, let's say this is just a random value, r. And she takes the commitment and sends it to Bob together with the claim that the polynomial evaluated at 1 equals 0. Alice needs to also compute the proof. So for this, she takes and computes the quotient polynomial. And this quotient polynomial is basically at the heart of every zk proof. So when you understand this, you basically it opened all the gates to understand all the zero knowledge proofs, how they work. So in my opinion, this is like the most important part of zk. So we have the quotient polynomial, which is calculated as p of x minus y, and y here would be y here would be 0, and this is divided by x minus a, and in this case a would be 1. So so this is what we do here exactly. We are just like putting the actual value of the polynomial instead of this representation, and based on the factorization rules, we can rewrite this exact polynomial as in this form, in the factor form. And when this is where we can easily divide the polynomial. So as we see, this and this part from the denominator and numerator cancels out. So what is left is polynomial x plus 1. And this is actually key, that if we calculate the quotient polynomial, that the result is polynomial. If the result is not polynomial, then when Alice will start verifying it, she will come to the conclusion that when the Bob will verify that Alice doesn't know the polynomial that she claimed to know. And the next step for Alice is to take this quotient polynomial and get a random point. Of course, in KZG or another, or actually in KZG it would be based on a secret value of SRS. But in the case of, on our case, we can say that this polynomial, the quotient polynomial, is evaluated on some random number. And as a verify algorithm, of course, it would be sent to Bob as well. And as a verify algorithm, Bob will have a commitment C, proof P, and the claim that the polynomial evaluated at 1 equals 0. So now the Bob can recalculate and check whether p of x equals the quotient polynomial times the term x minus y. So when we use our actual numbers and actual values, this is true, and based on it, Bob would be able to accept Alice's claims that she knows this polynomial that she mentioned at the start. And yeah, basically that is it from my side, so thank you very much. And if anyone has any questions, then please let me know. And here is address for my blog if you wish to follow me, feel free.